slides, we want to find the electric field due to an infinite line of charge. So this is the infinite line. It extends to infinity and down, and it extends to infinity up, and it has uniform charge per unit length. So we want to find the electric field at any point in space. So first thing we need to do is to use Gauss's law is to make a Gaussian surface. But we have to make it in a special way so that we can get rid of this dot product. So before we choose our Gaussian surface, we need to know what the electric field looks like. So what direction do you think the electric field would look like at any point in space, like this point in space? We can prove it from a kind of a symmetry argument. If you take an element of charge dq on this side, it'll make an electric field pointing downward like that. Then if you take an element of charge exactly the same distance on the other side of this central line to the point, then the electric field will be pointing this way. And you notice that when you add these two vectors, the y components will cancel and the x components will add. So you can conclude then that the electric field points radially outwards. The same kind of argument you can make with the symmetry argument that we did before for the sphere. If you take the infinite line of charge and you assume that the electric field doesn't point radially, say it points at some angle like this so that there's a parallel component of electric field. We're going to show that if you rotate the line and the field line, if you rotate everything 180 degrees around an axis like this, so everything rotates around an axis like this, what will happen? The field vector rotates, but the infinite line, when it rotates by 180 degrees, you get the same infinite line. So that means the charge distribution hasn't changed. So this is telling you that there's a different electric field vector that represents the electric field at this point for the same infinite line of charge, which cannot be the case. You can't have the same charge distribution giving you two different electric fields. So the electric field cannot have a component that's parallel to the line. The conclusion is, whichever way you want to prove it, that the electric field has to be pointing radially outward. If you extend the electric field to the line, this angle has to be 90 degrees. Okay, so this is the kind of geometry we have. If you look at it in 3 dimensions, this is the x and y and z axis. If you put your line of charge on the z-axis, then these are some of the representative electric field vectors on the x-axis and the y-axis. If you want to look at it a bit more closely, look from above. If you look from above downwards, then you see the x-axis is pointing this way and the y-axis is pointing this way, and the z-axis then is coming out of the page. So the line of charge in this case is just coming out of the page, so that's why you can only see the circle. And then you can see that the electric field lines point radially outward from the line in this way. So what shape Gaussian surface would you choose, and where would you put it to get rid of this dot product? Think about it for a couple of minutes before you proceed. So the solution is that we can take a finite cylinder. This green cylinder is a finite cylinder. It's a closed surface. It's our Gaussian surface. It's a mathematical surface. It doesn't exist in reality. We just use it to solve the problem. How do we take the finite cylinder? Well, if you look on the top face or the bottom face of the cylinder, let's take an element of area on the top face. Of course, the area vector points perpendicular to the area and it points from inside to outside, so it points upwards. But the electric field vector points radially outwards, as we showed before. The angle between them then is 90 degrees. For the bottom face, the same thing happens. The area vector, if you take an element of area like this on the bottom face, the area vector points perpendicular, but since this is the bottom face, the direction from inside to outside is downwards, so the area vector points downwards here. And still, the electric field vector is radially outward, so the angle is 90 degrees. Okay, what about the sides? If you make an element of area on the side surface here or here, doesn't matter where you make it, the area vector points perpendicular to the surface over here, and the electric field points radially outwards. And from the geometry, it's clear then that the area vector and electric field vector point exactly in the same direction. So the angle is 0 degrees. And this is exactly what we want to get rid of the dot product. So let's summarize what we said. This integration of a closed surface is cut up into an integration over the sides, integration over the top, and integration over the bottom. The integration over the top and the bottom give you 0y because the angle between electric field and area is 90 degrees. And the only term then that survives is integration over the sides. Now, integration of E dot dA is E dA cosine theta, and since the angle between the electric field and area vector is 0 everywhere on the surface, then theta is 0 and cosine 0 is 1, so now we got rid of the cosine. The other argument is, if you go anywhere on the surface of this cylinder, the electric field vector, the magnitude should be the same. If I go over here or over here, anywhere on the same radius, on the cylinder, on the sides, at the same radius, the electric field magnitude should be the same from symmetry. So that means that I can take E outside of the integration, and I'm left with integration of dA over the sides. Of course, if you think about this side surface, you can cut it at some point and then make it out into a big rectangle. The length of the rectangle will be the circumference of the circle, 2 pi r, and the height of the rectangle will be L. So that means the area, the side area, is 2 pi RL. So we substitute the side area and you get the final expression. For the left-hand side of Gauss's law, you get E times 2 pi RL. What about the right-hand side of Gauss's law? The right-hand side of Gauss's law is asking you to find the charge inside the Gaussian surface. So what is the charge inside the Gaussian surface? Well, if you look at the charge that I made in purple here, that's the exact amount of charge inside the surface. How could you represent this mathematically? Well, we know that the charge per unit length on this cylinder, on this line of charge, is lambda. If you multiply lambda times the length of the Gaussian cylinder, that will give you the amount of charge inside the Gaussian cylinder. So it's lambda times L. So we substitute the right-hand side lambda times L, and the left-hand side we have it over here. If you cancel the terms, you get the final answer that the electric field equals to lambda over 2 pi epsilon naught r. So the electric field goes like 1 over distance for an infinite line of charge.